Okay, thank you. Thanks for the invitation. So I've never been to Trento, so that's hopefully next year I will have a chance to come in person. Well, if there is next year. I will talk about something that has occupied my large fraction of my time in the last year or so, and this is beta transitions. Yeah, but this what I will talk about is based on a paper that appeared almost a year ago with Martin Gonzalez Alonso and Oscar Navidjet, and also a paper that is in preparation that is hopefully will appear this month, also with Martin Gonzalez Alonso, Aydin Palavlich, and Antonio Rodriguez Sanchez. So before I start, why is it? Before I start, let me just show you, because this is a workshop where we can discuss things freely. Let me just show you completely unrelated plots. Yeah, so I will talk about precision measurements. And now we have these two ways of exploring the new physics, yeah, either via a precision measurements at the low energy frontier, like, for example, measuring of the neutron EDM, which is shown here, or with high energy colliders. So if you look at the rate of progress, yeah, of the precision measurement, you see that it's pretty constant. Yeah, I mean, you could fit the straight line to this quite with good enough chi-squared, and this is how the sensitivity of the neutron EDM has been progressing in the years. This is the last measurement, the most precise measurement from the UCN collaboration. This is a projection for the future, yeah, when ESS is built, and this you see that we have this Moore's law, that there is a log of progress in is exponential, yeah, in this domain. And then of course this exponential progress also translates into exponential progress of in probing physics at a high scale. So if you translate this measurement into coefficient of an operator in the standard model effective field theory, which would be this kind of operator with some coefficient d that depends on new physics according to various hypotheses, either as v over lambda squared, where v is the 246 GeV, the weak scale, or is proportional to the quark mass, or proportional to the quark masses and divided by a loop factor. So with different hypotheses, you get difference in new physics scales that you actually probe. But yeah, of course, in any of these hypotheses, yeah, the sensitivity is growing very quickly, and even in this most a conservative hypothesis, you're probing the scales that are much above the direct and indirect electricity reach. Yeah, you're probing the scales of order 1 PeV. The same Moore's law, yeah, is applying to the colliders now. I mean, it has been applying to the collider. It's also exponential growth of energy. Yeah, so we could see like from 70s, yeah, to the LHC. It also follows more or less a straight line. Yeah, so that was fantastic. Yeah? And most of what we know about fundamental interaction, yeah, we learned from these high energy colliders. However, the difference is that if you now project into the future, yeah, then you're getting this this kind of a curve, yeah, that is sort of flattening. Yeah, and for the lepton colliders, it might be even going down. Yeah, so that's maybe that's the effect of the fit. Yeah, but let's not put too much importance on it, but clearly, yeah, this exponential rate of progress on the high energy frontier is going to stop for a while. So this gives you this shows that this doesn't mean that we should not build high energy colliders or anything like that. Yeah, this means that the importance of low energy precision measurement will be growing, and in the next 10-20 years, yeah, this importance here will be even will grow even more. So today I will talk about the beta decay. Yeah, so as one of this example of low energy precision measurement, actually very low energy from the point of view of particle physicists. The typical momentum exchange here is of the order of 10 MeV, so something really, really low. And at the quark level in the standard model, yeah, this process is mediated by the W boson, by the weak interactions. Yeah, one quark turns into another quark, and what appears is the electron and neutrino. If you go to lower energies, yeah, at the nucleon level, you have a transmutation of a neutron into proton and electron neutrino, and at the nuclear level, you have transmutations of different of nuclei into another with the same mass number, but you're changing the charge of a nucleus. So this process was very important historically because it was essential for understanding this, that the fact that parity is not conserved in nature. And then it was also essential for working out the structure of weak interaction in the standard model, the famous V-A structure of weak interactions. But its importance is also remains until today, as we will discuss in a moment. This gives you this beta decay gives you the most precise measurement of the CKM element VUD, so the 1-1 element of the CKM matrix, and which is one of the fundamental parameters of the standard model. So that's it's maybe surprising, yeah, that from something that you imagine is so dirty and so full of uncertainties, you're getting the most precise measurement of some fundamental parameter. Yeah, but this is the case. And another thing I will discuss today is that this gives us beta decay gives us a competitive and complementary to the LHC constraints on new physics coupled to first generations of quarks and leptons. So it's constraining this the type of new physics, such as, for example, leptoquarks. Leptoquarks are very fashionable today, and if leptoquarks exist and if they couple to first generation, they might show up in beta decays, or something maybe more common, less fancy, is right-handed W boson. That's another time something that the W boson coupled to right-handed quarks. That's another thing that could show up in the beta transitions. So this formalism has been, of course, developed since Fermi in the 30s, yeah, and basic facts about beta decay were understood in the 50s, and then I think by the mid 70s, yeah, also this all the effects that are relevant for present-day experiment, all the standard model effects relevant for present-day experiments have been worked out. But in this talk, I will talk about this well-known physics and in a bit different language. So I will try to connect to the particle physics community more, and I will sort of formulate this the physics of beta decay in the language of effective field theories. So my assumption here is that there is no new degrees of freedom at the very low energy scale, so that at the energy scale of, let's say, 10 MeV, there's no new particles that could be relevant for beta decay. And then if this is true, if this is borne out in nature, then I can use the effective field theory. And I will discuss how I can connect the effective field theory for beta decay to effective field theories that are commonly used in particle physics, such as the SMEF or the WEFT, the effective theory below the weak scale. So the basic picture, yeah, of this for this talk, yeah, is that there is something that we don't know up there, maybe at the scale of 10 TeV, maybe higher, and then we will descend the ladder of effective theories, yeah, through the standard model to the quark level, to the effective theories below the electroweak breaking scale, to the effective theories at the hadronic level, and then the effective theories at the nuclear level. And from here, we will compare to experiment, and then we try to go back and learn something about the physics at the very, very high scales. So yeah, if there is no questions about it, yeah, I will start with discussing with this the formalism for beta decays in the language of effective field theories. At the highest scale, so what is in this what is relevant here for beta decay? Yeah? In the standard model, the relevant physics, yeah, is the W boson, that it couples to the quarks and the left-handed quarks and couples to left-handed leptons, including the neutrino. And this is the mediator, yeah, of beta transition from the standard model point of view. But if you are at very high scales, yeah, there could be other degrees of freedom that equally well contribute to this. Yeah, there could be W prime bosons, just a heavier cousin of the W boson. There could be a leptoquark. Leptoquark looks like that, yeah, and this leads to the same diagram, but of course in a different structure. Leptoquarks coupled to a lepton and a quark, yeah, so they sort of swap. You have to swap the external legs, yeah, to make the correct diagram. And another possibility, yeah, is you have a right-handed W boson and you have a mixing between the two, and then effectively what happens is that this you can connect to the right-handed quarks instead of the left-handed quarks, as is the case in the standard model. So that's the physics at the very high scales, but of course that's not what we want to use to describe physics at very low energies of the order of 10 or 1 MeV. So we descend down this ladder, and the next step, yeah, is that when you integrate out new physics, yeah, we have the well-known SMEF, yeah. So we have standard model degrees of freedom plus higher dimensional interactions, and then there is a large set of this higher dimensional interactions that will be relevant for beta decays. Yeah, so for example, this kind of operators with the Higgs current and quark current, or Higgs current and the lepton current, or 4 fermion operators with 2 quarks and 2 leptons. Yeah, all of this contribute to the beta transition. We now, how does this operators connect to what was I just talking about, to the physics at the higher scales? Yeah, so for example, if we have a W prime, we would generate this kind of 4 quark operator with, so for fermion operator with 2 left-handed quarks and 2 left-handed leptons, with the Wilson coefficient that is of the order of the coupling strengths squared over the mass of the W prime squared. If we have a leptoquark, yeah, on the other hand, then we will generate this operators, this 4 fermion operators, yeah, with a different tensor structure than what we would get for the W prime. So this so-called tensor interactions, or two kinds of scalar interaction, yeah, with a different structure, and different. There's also different families of leptoquarks, and they would give you different pattern of this operator. So if you can measure these operators, if you can measure this Wilson coefficient in an experiment, you can determine them somehow. You can learn what is quite precisely pinpoint, yeah, what is the particle that lives at the high energy scales and gives you the dominant contributions to this process. For the right-handed W boson, you would get this operator, yeah, with the Higgs current coupled to the right-handed quarks. Yeah, so that's another. So basically, every kind of new physics give you a distinctive pattern of this operator. Yes, and if you can measure it, yeah, you can find out, yeah, what's up there. But again, here with an energies of 100 GeV, yeah, so that's much larger than the scale of our experiment. So we have to go down this ladder, and this we go below the electroweak scale. And the thing is that once you do that, yeah, the physics description simplifies quite enormously, because here you have at the leading order in this effective theory, yeah, you have very few. You just have 5 different operators that could contribute to beta transitions. You don't have W boson. W boson has been integrated out, so it's only contact interaction that could contribute here. And so we can have this V minus A type contact interaction that we have in the standard model. So if all epsilons are 0, yeah, that is the absence of physics beyond the standard model, but you still have this V minus A interaction, of course, from integrating out the W boson. But then if you have new physics, yeah, you can have any of this new other kind of interactions that are allowed by Lorentz symmetry, like V plus A. So this is the interaction with right-handed quarks, or tensor, or scalar, or pseudoscalar. And so that this is this 5 distinct possibilities. So you have basically all of nuclear physics, or all of the physics of the beta transitions can be described from this AEFT point of view by this 5 parameters. Yeah, then there's nothing else that is relevant at this point, from the point of view of fundamental physics. And again, you want to measure from experiment the values, the range, the confidence intervals here for this parameters epsilon to learn about new physics at the high scale. So let's go one more step down in the ladder of this, and this we want to go to the level of nuclei. And the one thing that is worth pointing out here, yeah, is that the characteristic energy scales for beta decay, which is of the order of 1 to 10 MeV, depending on the process, is much smaller than the nucleon mass. So the effective theory that is appropriate for this for describing these processes is non-relativistic. So it's something slightly different than what we are used to in particle physics, or in high energy physics. So the rules are a bit different. So it's still an effective theory. There is some expansion, but the expansion now will be in the spatial derivatives, or in 3 momenta. So the 3 momenta of the part in a convenient reference frame, the 3 momenta of the particles involved in this process will be small, and then you can make an expansion in the 3 momenta at the level of the Lagrangian. This will be the expansion in the spatial derivatives divided by the nucleon mass. And this parameter, yeah, this is a small parameter, so you can perfectly do an expansion in this. It can be something like 0.01 or less, yeah, and then depending on the process. So this is basic of our EFT. So we write the EFT Lagrangian in this fashion. So some leading term, subleading term, and so on, with each with more derivatives. And in the bulk of this talk, I will focus on the first term in this expansion because it contains the most important physics. And maybe if I have time at the end of the talk, I will mention what happens if you venture to the next term in this effective theory expansion, yeah, with 1 derivative. But for the moment, let's stay at the 0 derivative level. So our effective Lagrangian has no spatial derivatives. And then if you want to write the most general set of interactions, yeah, that are rotational invariant and contains one proton field, 1 neutron field. These are non-relativistic proton and neutron fields, and the relativistic electron and neutrino field. And there is only 4 ways you can write it down, and 4 non-equivalent ways you can write it down at the leading order of effective theories of the effective theory. So you have your problem further reduces to having only 4 parameters, yeah, which here I denote as CV, CS, CA, and CT. These are the Wilson coefficients, yeah, of my EFT, which again I will try to measure from experiment. Another simplification is that in this effective Lagrangian we have only 2 different bilinears of the proton and neutron fields that can appear. This corresponds to something you might have heard either in physics classes or in if you're reading the nuclear literature. This corresponds to Fermi and Gamow-Teller transitions. So if you write down an amplitude for the beta decay, it will have this form, and then there will be a nuclear matrix element. Yeah, so you have to sandwich this proton and neutron fields between the nuclear states. And this matrix elements are called Fermi matrix element for this bilinear, and the Gamow-Teller matrix element for this bilinear. This is a big simplification, because instead of having 5 different tensor structures, yeah, in the non-relativistic EFT you have only 2 different tensor structures at the leading order Lagrangian. One could also actually, this matrix element can be calculated from first principles, just from group theory, using the isospin symmetry. You can write down that for any nucleus, you can write down the value of this matrix element, just knowing the quantum numbers of the nuclear states. And this Gamow-Teller matrix element is more tricky, so you cannot calculate from first principles. It will be like some sort of nuisance parameter in your feeds later, yeah, because this is something that you have to determine also from experiment. You cannot it's calculated with any decent precision from theory. But yes, in any case, yeah, this problem of calculating the amplitude, yeah, is reduced to these 2 matrix elements and 4 unknown Wilson coefficients, yeah, that we have to somehow measure from experiment. Now, how does it connect to what I was talking before? Yeah, so we can connect this Wilson coefficients to the coefficients of the quark level Lagrangian. So here on the right hand side, I just remind the quark level Lagrangian, yeah, with all these relativistic tensor structures, v minus av plus a tensor scalar pseudoscalar, and here are the Wilson coefficients, yeah, of the non-relativistic EFT for beta decay. And here is the connection, yeah, between the map between the parameters of the 2 EFTs. So this will we have a dependence, yeah, on the VUD element. V is basically a Fermi scale in a different disguise. So this how the Wilson coefficient connects, yeah, we see here, yeah, we see that these 2 Wilson coefficients will be non-zero in the standard model limit also, because even if you put epsilon L and epsilon R to 0, these are non-zero. On the other hand, this CT and CS, if there is no tensor or scalar interactions in nature, yeah, then this will be 0. So in the standard model, you only have 2 Wilson coefficients. But yeah, you will not be assuming that. Yeah, we'll be more agnostic about it. Another thing that enters in this map is the so-called nuclear charges, which again, this is something that you cannot calculate from first principles. It's some inherently non-perturbative parameter. For GV, for the one here, you can actually show that it must be 1 to the precision of 10 to minus 4 from isospin symmetry. And on the other hand, yeah, there is no such isospin symmetry principle for the other charges. So you have to calculate it from the lattice. And we know this with these charges we have with about 10% precision. Then we also, because the precision of the beta decays is quite impressive now, yeah, you have to include in this map these radiative corrections. So there is this effect of radiative corrections here included, which is of the order of 2.5%. There has been a little bit of in the recent years, there was quite a lot of discussion what is exactly this value, because it's something that is not easily calculable. You have to use some also non-perturbative input to calculate these radiative corrections, and this is the value from Goldstein and Tseng that was obtained using some dispersion relation techniques. And this is the most precise value on the market for the moment. So this, you have the map, yeah, you can connect this non-relativistic EFT to the quark level EFT, and then there is a map between this quark level EFT to the SMEF, yeah, but I skipped, I wasn't discussing it, yeah. So you can go all the way up. Once if you measure these parameters, yeah, from experiment, then you can determine this epsilon parameters, then you can determine the SMEF, the Wilson coefficients, and then you can determine the parameters, the masses and couplings of the new physics at some high scale. Okay, so this is the the setup that I will be using. So I will be using this non-relativistic effective Lagrangian with 4 unknown parameters, and I will try to determine this Wilson coefficient from experiment, and then go back and using these maps also determine the parameters of the higher level EFTs, yeah, from the knowledge, yeah, of this parameters. So if again there is no questions, yeah, I will move to the next part of the talk, which is discussing the observables. Yeah, so what observables do we have to actually determine this parameter? So in this, if we're looking at the beta decay, this is a 3-body decay. So the phase space is 5-dimensional. Yeah, we can parameterize the phase space by the energy of a particle, one of the particles, which is usually chosen to be the energy of the beta particle or electron or anti-electron, and angles of the direction of where the electron moves and where the neutrino moves with respect to some chosen axis, which is most often the polarization axis if you if the parent nucleus here is polarized. So of course we never observe in this experiment, we never observe neutrinos, so neutrino just flies away undetected, but we do observe the momentum of the daughter nucleus, so we can reconstruct also the momentum of the neutrino from this information. So usually you just assume you know the momentum of the neutrino from the kinematics. And then the most general form, yeah, that you get at this leading order, yeah, of this differential distribution has the following form. So there is some function here of the electron energy. It's not important for our discussion. Then there could be corrections, yeah, to the shape of this function by so this is what standard model predicts for the shape of the energy spectrum. And this is so-called Firth's term, yeah, which arises in the presence of physics beyond the standard model and changes the shape of the spectrum. Next, you can look at the correlation between the direction of the electron and the direction of the neutrino, and this is this little a correlation parameter, and that's routinely measured in experiment. Another thing that is routinely measured is the correlation between the direction of the polarization and the direction of the electron, and this is the big A correlation. This, by the way, was the correlation that was measured by Wu to show the violation of parity, and this B correlation is the analogous one, but the correlation between the polarization and the direction of the neutrino. Then there is also the C correlation that, to my knowledge, was never measured. It's something that appears that in principle is there, but is never measured in experiment. And then there is also a D correlation, which is the triple correlation, and this is a CP violating parameter. So in this talk, I will not talk about CP violating observables in this, but in principle, you can measure also in beta decay CP violating observable, which is this D parameter. And if in the standard model, it's 0 to up to some subtle effects. And if you measure this to be non-zero, yeah, then of course you discover new physics, yeah, because the contribution to the D parameter from CP violation in the standard model are too small to be ever detected. Okay, so this thing you can different correlations, yeah, you can express them by different combination of this Wilson coefficients. So if you measure all these correlations, yeah, so ideally, yeah, you measure all of them, and then you can disentangle different Wilson coefficients, yeah, by using these formulas. One more thing is that is worth maybe to think. So the language used in nuclear physics is a little bit different than what we have, what we used to. So when we usually talk about if we measure the lifetime of a particle or total decay width. On the other hand, in nuclear physics, it's what is often used is so-called half-life, which is just log 2 over gamma. Furthermore, because the decay width depends on the phase space, and the phase space is very different for different transitions, it is very common to factor out this phase space factor and to define so-called FT. So that's to more easily to compare different kind of transitions. And then furthermore, one can also factor out certain transition dependent radiative corrections, and then define this big FT, and this big FT will be connected to the parameters to the parameters that enter the total width in this particular way, where x depends on this on the Wilson coefficients of the effective Lagrangian, and also this b, the Fields term, depends on the Wilson coefficient of the effective Lagrangian. Yeah, so and there is no dependence, so this expression is pretty universal in a sense that it's the only non-universality that enters here, is via this average of electron mass over electron energy, which only appears in the presence of new physics, in the presence of this Fields term. So this is just so that you more easily understand the language that will be used, or what kind of data are provided, by nuclear physics. So FT is basically the glorified version of a lifetime or the total width. So it's just a different way of reshuffling the same information. Okay, so what data we have? So we have this will be the things that we'll put in this big cauldron and get the global feeds to the parameters of our EFT. And first, the first kind of transitions are that I will talk about is so-called super allowed 0 plus beta transitions. So there is this again some part of the nuclear physics idiosyncrasy. So there is we will be talking about so-called allowed transitions, which are the ones that are mediated by the Fermi and Gamow-Teller matrix elements. There is also forbidden transitions, which are not forbidden, but mediated by other matrix elements and therefore suppressed. And super allowed means that the lifetime is small for the standards of nuclear physics. So super allowed 0 plus to 0 plus beta transition. So there is this set of this different nuclei which undergo. This is a subset of the nuclei that undergo this beta transition, starting from the 10 carbon to going to 74 rubidium. Although this is all this Mendeleev table that is entering here. This data have been compiled by this two people, Hardy and Towner, which have been doing actually this for, I don't know, maybe 30 or 40 years. Every 5 years, they give you a new updated combination of this measurement. And this is, if you look at it, this is quite impressive. So the measurement of FT, which, as I was explaining, is basically a measurement of the lifetime, is in some cases you have a precision that is better than per mil. So you have a nuclear physics measurements with better than per mil precision, which is thanks to very, very hard work, both by experimental collaboration, but also by this people that factor out various radiative corrections and to get to this clean number. And the thing that is worth looking at is, so this is the rationale for defining FT, is that this measurement in different nuclei gives you the same value within the errors. And the reason is, that this FT is defined such that it's should be the same for this 0+ to 0+ transitions in the absence of new physics. So to turn it around from the fact that this FT measure is measured the same in all the different transitions, you can conclude that there is no indication of new physics in this data. So if there was new physics, it would enter via this Firth term that is proportional to this average of ME over EE, which is different for different transitions. So then it would, if this term was non-zero, this would lead to FT that is different in the different transitions. But because this FT looks the same, this is a constraint on this how big this Firth term can be. What can you actually? So what can you learn from this data? So because this is spin zero transition, things simplify actually. So I was talking here that there is this Fermi and Gamow-Teller matrix elements, but Gamow-Teller matrix element, because it's a vector, it cannot. It's zero for spin zero transitions. So part of this contributions to this from the Gamow-Teller matrix element is zero. So things simplify. Here, sorry, I forgot to remove part of this formula. So these are the parameters of interest. So the overall normalization is the sum of the vector and scalar Wilson coefficients, and the axial and tensor Wilson coefficients don't enter here because they would enter via this Gamow-Teller matrix element, which is zero. And this B term is proportional to the product of vector and scalar. There's also the CV minus and CS minus that I forgot to remove for the sake of this talk. They arise in the presence of right-handed neutrinos, but for the moment we assume that there is no right-handed neutrinos. So these are also zero, and you should unsee them. So basically all this data will give you will determine these two Wilson coefficients CV and CS, and from the fact that this Firth term is consistent with zero, you can disentangle the two and put a constraint on the scalar interactions. Next, very important piece of data is the neutron decay, and for the neutron decay we have a lot of different measurements of correlation. So for the neutron decay we have both Fermi and Gamow-Teller matrix elements, and there is a lot of interesting more interesting physics that you can do. And the table that I have here was copied from the paper a year ago, and this crosses show that since 1 year there was already quite an important updates of these measurements. So for example, in this case, error was for this little a correlation, the correlation between the direction of the neutrino and electron. The error has been reduced by a factor of 2. Also for the Neutron Lifetime, the error has been reduced by a bit. And another thing to see is that for this big A correlation, the error is at the level of 10 to minus 4 also. So that's another impressive kind of measurement. So this is the neutron data, and you might have heard that there is a little bit of a controversy about the Neutron Lifetime here. So this is the different measurements of the Neutron Lifetime showed on the historical scale, and there is two kinds of measurements of the Neutron Lifetime. One is called a bottle, where you put neutrons in the bottle, from the theory's point of view, magnetic trap more precisely, and you just wait and see how many of them survive after a given time. And then there is a beam where you have a beam of neutrons, and you look for the decay of these neutrons into protons. And these two kinds of measurements, they give you slightly inconsistent results, but also there is a little bit there has been a lot of discussion about this inconsistency between the beam and bottle, but in reality there is also a big scatter between the bottle and bottle. Yeah? So there is, if you want to, the inconsistency between this the bottle measurement is almost as large as the inconsistency between the bottle and the beam measurements. And if you take into account the fact that these have smaller errors. So what one does in this situation is that so the PDG particle data group has a procedure as to what to do in these cases. So if you don't know who is wrong, you just penalize everyone. So you blow up the errors until the combination has a chi-squared equal 1 per degree of freedom. And so in this case, for the neutron, one has to blow up the error by a factor of 2.2 currently, yeah, to accommodate to follow this procedure. So the error for the neutron lifetime is 2 times larger than it should be given the experimental precision. It's just because of this inconsistency between different measurements that the error has to be increased by a factor of 2. If this inconsistency is worked out, which fortunately it will be in the near future, yeah, then the error will shrink further, and that will become one of the most precise measurements, yeah, in this beta transitions. This is slightly less known, but there has been a similar situation for the measurement of the big A correlation. So this is this correlation between the polarization and the direction of the outgoing electron. There was also inconsistency between the earlier measurements and newer measurements, yeah, so which led to a much larger error. This was the value that was given by PDG I think 2 years ago. But given the new precise measurements, then the importance of this older measurements became less, and they can be discarded from this combination. And then once you do that, yeah, then the error is just goes down by a factor of 5, and this becomes again very, very precise measure. Okay, so this is this is neutron. Except for the neutron, there is a lot of measurements in different nuclei that have per mil to percent precision, and we also include them in the feed. But let me not go through it because they have less importance. They are slightly less precise, and they do not affect the results of the feed in an important way. Let me just say there is one more thing that I want to discuss here is so-called mirror transitions. So this is another group of measurements that is we include in our feed. Mirror transitions is the transitions between the isospin half, same spin, and positive parity nuclei, and they are. So neutron decay is technically also a mirror transitions, but we don't put it in this box. Yeah, we call mirror transitions only nuclear transitions and not the neutron decay. And these are mixed Fermi gamma-Teller transitions. So they will depend on this unknown matrix element of a gamma-Teller matrix element, which will enter a feed as a matrix as a mixing parameter rho, which is something that we don't know. We have to get it from the data. So there is a lot of this mirror transitions. That maybe the most famous one is the tritium decay, but there is many more of this type. The problem is that in this case, and again, sorry that I forgot to remove this Wilson coefficients that are relevant in the presence of right-handed neutrinos. So try to unsee them. In this case, the lifetime will depend not only on the vector and scalar Wilson coefficients, but also on the axial and tensor. And the relative importance will be proportional to this mixing parameter rho, which is unknown. This is something we don't know. We have to determine it from experiment. So one way to determine it, yeah, is to have different kind of observables, yeah, for the same mirror nuclei. And it turns out that there is smaller subset of 6 mirror decays, which have the for which some lifetime and some other correlations has been measured with a good precision, and this allows one to determine this mixing parameter rho and something else, some Wilson coefficients at the same time. So one can disentangle this nuisance parameter rho that is comes from this unknown gamma of Taylor matrix element, and actually learn something also about the fundamental parameters of the EFT Lagrangian. Okay, so this is the data. So let me just present you the fit results. Yeah. So what do we learn from this? So first, let's do the fit in the standard model limit. In the standard model limit, there is no scalar and tensor interactions. So we assume the absence of new physics, and we only have this vector and axial interactions here that enter in the EFT in this way. So we have these 2 Wilson coefficients, and we can determine them from the data. As I said, we also included this mirror transition. So we have this 6 nuisance parameters, which are not interesting from the fundamental point of view, but they might be interesting also from the point of view of nuclear theory. Yeah? Because in principle, if you know how to solve nuclear theory, you would also be able to calculate this mixing parameters. And what one can see is that in this limit, the accuracy is indeed very, very impressive. Yeah, it comes at it is at the level of 10 to minus 4. This is dominated for CV, is dominated by the super allowed 0+ to 0+ beta decays, because each of them has a precision of order 10 to minus 3, but there is many of them. So if you combine them, you're getting something like 10 to minus 4. And CA is the gives you the measure is dominated by the measurement of the polarization of the beta asymmetry. So this big ape correlation in the neutron. So these are the 2 pieces of data that dominate this fit. Yeah, but there is everything is in there. Yeah, and also slightly affects the errors and the central values. So now what does it mean? Okay, so we have this measurement. So this is given in the units. So these are dimensionful parameters. They are in the units of 1/v². They are order 1 in this units. Yeah, so this is not surprise here, because in the standard model they are generated by the W boson exchange. Yeah, so this is the natural value. And now we want to translate this into more fundamental parameters. So we go back to this map, and we can connect the CV and CI to 2 unknown parameters. VUD, we don't know VUD in the standard model, so this is one. And also there is a parameter called GA, which is the axial charge of the nucleon. So in this case, it's actually GA is known from the lattice, but it's known only with the precision of the order of 1%, because lattice for the moment cannot do any better. However, if you determine the same GA from the data, you're getting a consistent result, but with a precision of order 10 to minus 4. So a phenomenological determination of the nucleon charge is 2 orders of magnitude better than the lattice determination. So you can translate this measurement into measurement of VUD and GA, and this is the results. And as advertised, you have a measurement of VUD at the level of 10 to minus 4 precision, and this is the most precise measurement of the VUD that we have at the moment. There is, as I said, has been a little bit of controversy about this VUD measurements. So first, if you determine VUD from unitarity of the CKM matrix, so you take the measurement of VUS from K-on decays, and you're getting a value that is somewhat inconsistent. It was consistent before, but then there was a phase transition. Yeah, there was this radiative corrections were recalculated more precisely here, between here and here, and that pushed the value down. Then the errors were there were different groups that essentially confirmed this new determination. And this is the value that we have, yeah, which is also inconsistent with the, at the level of 2 sigma, yeah, with the unitarity of CKM matrix. But we have our errors are larger, yeah, because we're including additional layers of uncertainties that were pointed out in the subsequent papers to that one. So at the end of the day, yeah, you have the situation is now more or less stable. So we know that VUD that is measured in nuclear transitions is in slight tension with unitarity, but this tension, yeah, is not yet so important to cry that there is any need for new physics. You can also look at how this tension looks if you take in different part of the data. And so again, this is the value that you're getting from unitarity. And this is the value of the VUD determined not from a global fit, but from particular pieces of the data. So this 0 plus to 0 plus super allowed give you this most precise value that is in tension with unitarity of CKM matrix. On the other hand, for the neutron decay, the values are these three different values, yeah, are depend on how you treat the errors, whether more aggressively or less aggressively. But maybe the interesting thing is that if you look at the most precise measurement of the neutron lifetime and big A, if you take just this most precise measurement, you're getting a value that is consistent with unitarity. So neutron seems to be the key to understanding this problem of CKM unitarity that has evoked a lot of interest in the recent days. And if new measurements, more precise measurements of the neutron lifetime and also the beta polarization asymmetry, if they make this measurement migrate towards the unitarity value, then probably will conclude that there has been some systematic problem with this particular piece of nuclear data, and we will have to blow up the errors here and conclude that there is no problem with unitarity. Also, mirror decays, they have larger errors, but they are consistent with unitarity. And this is something that this has nothing to do with nuclear physics, but you can also measure VUD in pion decays with much larger errors. So this is not at the moment competitive, but there is no, of course, no, that doesn't point to any problem with unitarity. Okay, and the second thing is the second type kind of the fit that we can do. So first we did the fit only with the standard model parameters. Now we remove that assumption and we keep all the parameters, all the Wilson coefficients in the leading order EFT Lagrange. So we have enough data to measure all these parameters independently. And if you measure, if you do this global fit with 4 parameters, you're getting slightly larger errors for the standard model parameters. So the errors blow up by a factor of 2. Here, in both cases, I think they blow up more or less by a factor of 2. And in the same time, you're getting measurement of the scalar and tensor coefficients, which are consistent with 0, because this means that there is again no indication of new physics, yeah, because these are supposed to be 0 in the standard model. And the level of precision for this Wilson coefficient is 10 to minus 3. So per mil precision, which translates into good reach for new physics. Now, if we can again translate these measurements, of Wilson coefficients into measurements of the Wilson coefficient, the quark level Lagrangian. So we have this epsilon L, epsilon R, epsilon S, epsilon T, and this is a little bit tricky, because if one could notice, that what is actually determined, so we measure. This is what we measure in experiment, and this is the translation, of into more fundamental parameters of a higher energy EFT. Now, what we measure here is not exactly VUD and the axial charge GA, but some combination of the fundamental VUD and fundamental GA and these new physics parameters. So, for example, for the GA, you cannot, if you assume that there is new physics beyond the standard model, you cannot interpret the measurements from the global feed as a measurement of GA anymore. And what you really measure is a combination of GA and approximately shifted by the Wilson coefficients that is parameterizing the V plus A non-standard interactions in the quark level Lagrangian. So from the data alone, we cannot measure GA, but now we have a lattice. Yeah, so if we have a lattice, now if we use the lattice input, and this is the latest lattice input from FLAG with a 3% error, we can get the we can get this disentangle the two, and then we can get a measurement of this epsilon r parameter that parameterizes the V plus A interactions. So now if we disentangle everything, yeah, we're getting this constraints on the more fundamental parameters, epsilon r, epsilon s, and epsilon t. We're getting 10 to minus 3 Fermi level constraint, yeah, on this scalar and tensor interaction in the quark level Lagrangian below the electroweak scale, and we're getting a percent level measurement constraint on this epsilon r. In all of these cases, we don't see any evidence for new physics. So all in all, so if you now translate it into reach into new physics, yeah, so this of course depends, yeah, on the coupling strengths of new physics, yeah, which generates this Wilson coefficients. But so this I showed here. The scale I'm showing here in this plot is corresponds to this maximally strongly coupled new physics with G star equals 4 pi, but of course you can rescale it to a different coupling strength. So this is sort of maximal reach for new physics, yeah, depending on the what is the if the new physics couples as strong as it is technically possible. So you see that in this case we're getting the reach for new physics at the level of 100 TeV. If new physics couples, yeah, with perturbative coupling strength, then this 100 TeV will become 10 TeV. So this, for example, for laptop works, yeah, with order 1 coupling, yeah, we can probe them up to 10 TeV. Here we have a better reach for new physics, but it has nothing to do with nuclear physics. It is constraints on the pseudoscalar couplings from pion decays, and they are because of the effect called chiral enhancement. Yeah, they go even factor of 10 larger. So this is, so if you compare the two, yeah, the LHC reach, yeah, indirect reach. So for example, in the LHC, you can look at the Drell-Yan process, yeah, to probe the same kind of operators, and the two, both the LHC and the nuclear physics, yeah, will give you similar sensitivity, yeah, to this 4 fermion interactions between the quarks and leptons. So depending on how the two progresses, yeah, then if the precision of nuclear physics improves by another order of magnitude, yeah, then it will overtake LHC, but our LHC will also improve as more data is collected, yeah, at 13 and 14 TeV. Okay, so let me not discuss it. Let me summarize. I think it's 1 hour, so it's a good moment to stop. Yeah, and so what I wanted to say in this talk, yeah, is that nuclear physics is a treasure trove of data that can be used to constrain both the standard model physics, but also new physics beyond the standard model. We have, thanks to continuing experimental and theoretical progress, the accuracy is reaching like sometimes per mil or even 0.1 per mil for some observables, and that gives us access to new physics at the scales of 10 to 100 TeV. So what we did, what we are doing, yeah, is that we are using combining all the available data from different sources of different beta transitions. Yeah, we constructed a general 13 parameter likelihood for the Wilson coefficients of the EFTs, together with some nuclear level parameters, together with some nuisance parameters. And from that, we can determine all the Wilson coefficients independently in the low energy EFT, and then translate this likelihood into likelihood for the parameters of the higher order EFTs, like WEFT below the electroweak scale or SMEFT above the electroweak scale. So this is some ongoing project because the data is coming and the accuracy is improving basically every month. What we are doing on the theoretical side, which I don't have time to talk about, but in this talk I stopped at the leading order in the EFT expansion. And in the paper to come, we will do the sub-leading order, where there is additional interactions that appear that has to be taken into account, and they also can be determined from the data, and you can do more general fits that also include the effects that enter at the sub-leading order in the EFT. So I have two slides about it, but let me not talk about it for the moment, and if you can ask me about it either in email or in questions. So this is it for today. Thank you very much.
Thank you, Adam. I think it's time for the audience to ask questions or to raise points for discussions. You can raise your hand if you want, or just open the microphone. We are not too many, so should be ordered enough. I see a question. First was Francesco.
Yes.
Please go ahead.
Yes. First of all, I apologize. I'm sorry I could not connect from the very beginning of the talk, but by the way, I wanted to ask if, I wanted to ask if from these sub-leading corrections that you are going to compute, in my understanding, or are computing or are going to compute, if you expect that this could have an impact on, or what size of impact you would expect? Do you think this goes into the direction of reconciling let's say the small disagreement with the determination of VUD, for example, with unitarity, or the size of these?
No. So okay. So maybe to explain it a little bit better, I didn't explain it. So this subleading correction. So this is if you see the slides, this is the Lagrangian, the subleading level. Part of this Lagrangian appears in the standard model. Actually, this part, which is denoted here CFV, and this part, which is denoted CM, they appear in the standard model, and these effects are taken into account in the determination, by the experimentalists which do their experiment, because they are of the order of 10 to minus 3, so they are of the same level as the experimental precision. They have to be taken into account. So we are not really recalculating the standard model. I mean, we can recalculate it, the standard model effects in this formalism, but this is nothing new. What is new is that we can look at new physics entering at the subleading order, and this is what we will constrain in this upcoming paper. And as an example, for example, is one example that you can show here. There is this interaction called CP. Here, this is the first one here, and this arises from pseudoscalar interactions at the quark level. The pseudoscalar interactions, they don't enter into the leading order; they only enter into subleading order. So there is technically a new effect that enters only at the subleading order. So you don't see it if you stop at leading order, and it's a new physics effect that will appear at the subleading order. And you can do the fit to this pseudoscalar, and it actually turns out that you're getting decent sensitivity to the pseudoscalar, although it is much worse sensitivity anyway than what you get from pion decay. So it's a sort of curiosity at the end of the day. But this is just an example. Yeah, there will be more examples. Yeah, that we will show in the paper showing how new physics enters. Yeah, via subleading effects in the CFT. Yeah. But this will do nothing to alleviate any tensions, yeah, because all these effects are taken into account already by when this tension is claimed.
Then the role played by the VUD, what would be the role played by VUD in your analysis?
Well, VUD gives you just the we go back to the beginning, yeah, where I showed these Lagrangians. Yeah. So VUD gives you an overall normalization of the Lagrangian, yeah, in this language. If once you integrate out the W boson couples to the quarks with the strength proportional to VUD. So all the effective Lagrangian is proportional to VUD. So if you measure the strengths, yeah, the overall strengths, yeah, of the Wilson coefficient, yeah, you can translate it into a measurement of the VUD.
Mm-hmm.
If
Thank you.
Francesco is happy with the answer, we can move to Aldo's question. Otherwise, please go ahead.
Oh, I'm happy, thanks.
Okay, thank you. So I was curious about the parameterization and the results, including right-handed neutrinos. So apparently this is completely new. Does it mean that there are no other competing, at least at the same level, results for that? And second, what is the difference with a fit that only includes left-handed neutrinos? Is it a completely different thing, or?
Yeah. So in this talk, I was talking about the right-handed neutrinos in previous talks I was giving on this topic, but somehow the amount of information is always a bit too large, and I never managed to get to the right-handed neutrinos. Yeah, but right-handed neutrinos are in the paper that I quoted, yeah, on the first page. So if you look at this paper, yeah, there will be fits, yeah, with right-handed neutrinos there, and what is the effect of the right-handed neutrinos? Yeah, so if you look at the effective Lagrangian, for example, at this level below the electroweak scale, so this are all the interactions with left-handed neutrinos, and if you have right-handed neutrinos, you can have analogous interactions, but you just replace mu L with mu R. So it's like 5 new interactions that you can add to the effective Lagrangian. So you basically double the number of parameters in the effective Lagrange. Now, what is interesting is that in spite of the huge number of parameters, you get 8 new physics parameters, yeah, that you have to fit at the leading order. In this paper, we showed that you can, given the current data, you can fit them all. And you are getting also constraints on all these interactions involving the right-handed neutrinos, and at the same time in the interactions involving left-handed neutrinos. Yeah, so sort of all the possible, even if you assume that there is right-handed neutrinos, yeah, you can get still get all these you could all the parameters of the EFT can be independently constrained. On the other hand, in the amplitude, the right-handed neutrino contributions do not interfere with the left-handed ones, so they only enter quadratically. So the sensitivity is smaller. So while I was showing that you're getting a per mil sensitivity to the scalar and tensor interactions with left-handed neutrinos, you're getting only 10% or 0.1 sensitivity to interactions, to analogous interactions with right-handed neutrinos. So you can get constraints, but they are quite weaker, yeah, and they allow you for new physics with right-handed neutrinos right above the weak scale. You don't have to, it doesn't have to be pushed well above the weak scale. So that's the difference.
Yeah, okay, that was precisely my question because I wasn't sure if the constraint was strong on that sector. But so
No, it's weak. It's weaker, yeah, but they are non-zero, yeah. So in the sense that they are non-trivial, you're still getting constraints at the level of 0.1, yeah. So in the limit, in the range of validity of the EFT, yeah, you don't have to have very large Wilson coefficients, yeah, to get any effect.
Okay, thank you.
I invite other questions and comments. You can just raise your hand or open the microphone. I don't see raised hands, so let me ask one curiosity. How much are you relying in his analysis on the fact that this FT has been tailored to be universal except for possible BSM effects, this little b that you are
I think it's just how you cut it and splice the data, yeah. So it's so on the other hand, I do rely. So there is this. Here is this measurement. Yeah. So this measurement is not really an experimental measurement. Yeah. There is an awful lot of theory going into it. So the experiment measures really the half-life, and then these guys, Hardy and Towner, take this half-life, take this and take the determination, yeah, of this radiative corrections, subtract them away in such a way that you get this final product that is FT. So this FT, final product FT, is very convenient, yeah, to compare to the theory, yeah, because you can you have a very closed, simple expressions, yeah, on this for this FT in terms of the Wilson coefficients. But I have to believe that these guys did correctly all this dirty work, yeah, of removing this radiative corrections, yeah, from the data. So this so there is a little bit of a black box, yeah, that is from my point of view, and I never repeated the analysis, yeah, because this is something that you need to do for 20 years, I guess, to do it. And it is possible. There is some people criticizing this analysis that the errors might be underestimated, the systematic errors in this analysis. Because also it's a little bit more complicated. Not only relies on relative corrections, but also on nuclear models to some extent. Yeah, so you have to take some input from nuclear models, yeah, to get rid of certain effects. And it's possible, yeah, that all this CKM unitarity problem is because these guys slightly underestimate the errors, and the error is in fact factor of 2 or larger, and that. So this is a bit unfortunate, but as I was saying, we will know soon because neutron data are reaching the same precision, and they don't have this problem. There's no nuclear structure for neutron data, so all these problems that are that might be plaguing this Hardy and Towner analysis of 0+ to 0+ are not present for the neutron data. So in the year or two, I think we will know. Yeah, I think we will know if these guys maybe got it wrong, or we will know, or it will turn out that the CKM unitarity problem will persist even after we get new, very precise neutron data.
And is there a chance that B receives the contributions from Higgs boson? I was wondering, just looking into the fact that it's semi-dependent.
Not that I know. So like, so yeah, so this is an expression for B. So this is CV times CS, and then you have to go back. Yeah, CS is epsilon s in the quark level Lagrangian, and so this is so basically you probing this interaction in the quark level Lagrangian, yeah, the UD E bar nu L without any gammas, and then this epsilon s. Whoops, where were we? Corresponds to two operators, yeah, in the EFT, in the SMEF, yeah, which are these two in the last line. So yes, sorry, yeah, you see, yeah, you're right, yeah, you do get contributions from the Higgs boson, but of course it will be tiny, yeah, because it's if Higgs boson couples, with the strands proportional to the standard model Yukawas, this will be very, very suppressed, because you have to pay a price, not only the quark Yukawa, but also electron Yukawa. If these Yukawas are larger, maybe there is some wiggle room. But so, I never thought about this as a measurement, but it's actually funny, but you're right, that this is could be a measurement of the Higgs Yukawas too. But I think about it as a measurement of leptoquarks, because leptoquarks will generate, different leptoquarks will generate a different pattern of these two operators.
Okay, thank you. Anybody with any curiosity on how we have to go very low energy, apparently? I don't see anyone, and this means we either keep asking whatever you have in mind, or we have to wait 13 minutes before we can start the next talk. I'm happy to wait, but so we can fill this with more discussion. Maybe I can ask you another curiosity I have. Was you were discussing beta decays the whole time, and you never mentioned the beta decay for me, which is the muon beta decay. Is there anything, nothing to be learned from that measurement, which is, I think it can be precise, it doesn't have matrix elements from the nuclear world, etc. So maybe I'm maybe missing.
No, of course, no. So it's measuring. You are measuring different kinds of operators. You're not measuring VUD, and from muon decay, you basically measure the Fermi constant. So muon decay is not really a probe of new physics in the first approximation, because this measurement determines the Fermi constant, which is GF, which is related to this V. So V I define in terms of the Fermi constant. I never remember the formula, but this V is some square root of 1 over GF. So with some square root of 2's in random places. So in this sense, you do not constrain new physics in the muon measurement. In the second approximation, you can measure so-called Michel parameters in muon decay, and then so you go into differential distributions of the muon decay, not only lifetime but also differential distributions, and then you do constrain new physics. So you have the you have some you can get constraints on some additional 4 lepton operators. That's so 2 muons and 2 electrons. This is what you constrain. So I had a paper long ago with Kim Mimuni, a student of mine at the time, and there is, I think it was around 2015, and we did this analysis there, and you can get some meaningful constraints from muon decay too, if you look into the differential distributions. This is indeed something that is not pursued experimentally very much lately. So there might be something interesting.
I was trying to gather some literature during your talk, because I think Michel is basically coming from this Jackson at the same time as this Jackson paper in the mid-50s.
I don't really remember what is.
Anyways, I was aware of that, and I only found G Fermi measurements, as you said, not updated.
Yeah.
Okay.